March 7th, 1942, south of New London, Connecticut. The waters of Long Island Sound stretched grey and cold beneath an overcast sky. Navy blimp K-5 drifted silently at 200 feet, its massive envelope swaying gently in the Atlantic breeze. Inside the control car, radioman second-class John Mason watched a small metal cylinder tumble from the blimp's belly, its parachute blooming white against the dark water below. The cylinder hit the surface with barely a splash. Within seconds, its flotation device inflated, an antenna extended skyward, and somewhere beneath the waves, a hydrophone dropped into the silence. Mason adjusted his headphones and waited. Through the static came a sound that would change naval warfare forever. The rhythmic thrum of submarine S-20's propellers, running completely submerged 80 feet below the surface. The submarine crew had no idea they were being listened to. No idea that the ocean itself had just become transparent. The age of the sonobuoy had begun. 2 years earlier, as German U-boats prowled the Atlantic with near impunity, Allied commanders faced an impossible problem. Submarines were invisible. Surface ships equipped with sonar could detect them, but only at close range and only while moving slowly. Aircraft could spot surfaced U-boats with the naked eye or with radar, but the moment a submarine dove, it vanished. The ocean became a perfect hiding place. A U-boat captain under attack needed only to submerge to 100 feet and wait. Within minutes, the hunting aircraft would exhaust its fuel and depart. The submarine would surface, recharge its batteries, and continue its deadly work. In 1941, German submarines were sinking Allied ships faster than they could be replaced. The mathematics were brutally simple. If the trend continued, Britain would be starved into submission by mid-1942. The concept of an airborne listening device wasn't new. During the First World War, hydrophones mounted on ships had proven effective at detecting submarine sounds. But aircraft couldn't carry ship-mounted equipment. They couldn't hover in one place long enough to maintain sonar contact, and they couldn't communicate what they heard to other hunters in the area. Professor Philip Blackett, head of the British Admiralty's Special Committee for Anti-Submarine Measures, proposed a solution in May 1941. Create a self-contained sonar unit that could be dropped from aircraft, float on the surface, listen for submarine sounds underwater, and transmit those sounds via radio back to the aircraft. The idea was elegantly simple in concept but fiendishly complex in execution. The device needed to survive the shock of hitting water at terminal velocity. It needed batteries that could operate for hours in saltwater conditions. It needed a radio transmitter powerful enough to reach an aircraft miles away but light enough to float. Most critically, it needed a hydrophone sensitive enough to detect the subtle sounds of a submarine's machinery through hundreds of feet of ocean water. The British conducted initial tests but lacked the resources to develop the concept fully. America's entry into the war in December 1941 changed everything. By January 1942, German U-boats had launched Operation Drumbeat, sending submarines to prowl the American East Coast. In the first 6 months of 1942, U-boats sank over 400 ships in American waters. The vessels were torpedoed within sight of shore, their burning hulks visible from beaches. The water burned with spilled oil, bodies washed up on tourist beaches. The American public watched their coastline become a graveyard. The United States Navy didn't have enough escort vessels to protect the merchant fleet. They didn't have enough patrol aircraft. They didn't have enough of anything except desperation. In July 1941, before America even entered the war, 3 universities had been tasked with developing anti-submarine technologies. Columbia, Harvard, and the University of California each established naval research laboratories. Their mandate was simple: find a way to detect submerged submarines from aircraft. The Columbia University team, working at the Underwater Sound Laboratory in New London, Connecticut, focused on the sonobuoy concept. The lead engineer was Philip Mason, a civilian acoustics expert who would become known as the father of the modern sonobuoy. Mason's team faced extraordinary challenges. The device needed to be expendable because aircraft couldn't land to recover it. It needed to activate automatically upon hitting water. The hydrophone had to be neutrally buoyant to hover at the optimal listening depth. The radio frequency had to be compatible with existing aircraft receivers, and the entire package had to be manufacturable by the thousands. The first prototype sonobuoys were crude affairs. Mason tested early models by throwing them off bridges over the Thames and Connecticut rivers. Local Federal Communications Commission monitoring stations detected the transmissions and initially suspected enemy spy activity. The panic that ensued nearly shut down the entire program before it began. By early 1942, Mason's team had developed a working prototype designated the AN-CRT-1. The device was cylindrical, about 5 inches in diameter and 3 feet long. It weighed approximately 20 pounds. The top section contained a radio transmitter, antenna, and flotation bladder. The middle section housed batteries. A seawater-activated switch turned everything on upon immersion. The bottom section held the hydrophone suspended on a cable that allowed it to hang 30 feet below the surface. The March 7th test with Blimp K5 and submarine S-20 proved the concept worked. The sonobuoy detected the submarine at ranges up to 3 nautical miles. The radio signal reached the blimp receiver clearly at distances up to 5 miles. But detection alone wasn't enough. The early sonobuoys were omnidirectional. They could hear a submarine but couldn't determine which direction the sound came from. Multiple buoys were needed to triangulate a position, and even then the process was imprecise. The limitations were frustrating but acceptable. For the first time in history, aircraft could hunt submarines underwater. The invisible was becoming visible. Production began immediately. RCA, General Electric, and several smaller electronics firms received contracts to manufacture sonobuoys. By June 1942, the NECRT-1 became the first operational sonobuoy in Allied service. The US Army Air Forces, desperate for any advantage against the U-boat menace, ordered 6,410 units. The Navy, initially skeptical, ordered 400 experimental units for testing. The first combat use came in August 1942. Army B-18 bombers operating from bases in Newfoundland began carrying sonobuoys on anti-submarine patrols. The results were mixed. Ocean conditions were far harsher than the calm waters of Long Island Sound. Wave action created tremendous background noise that obscured submarine sounds. The hydrophones picked up everything: rain hitting the surface, fish, whales, snapping shrimp. The thermal layers in the ocean that bent sound waves unpredictably. Operators needed extensive training to distinguish submarine propeller cavitation from natural ocean sounds. But when conditions were right, and the operators were skilled, the sonobuoys performed miracles. An aircraft could spot a U-boat on the surface, watch it crash dive, then drop a pattern of sonobuoys around the last known position. The buoys would form an acoustic net. When the submarine tried to slip away, its propellers would be heard on one or more buoys. The aircraft could vector surface ships to the exact location, or attack with depth charges itself. For German U-boat crews, the change was subtle at first, then terrifying. Through 1942 and into early 1943, U-boat captains noticed an unsettling pattern. Allied aircraft were finding them underwater with impossible accuracy. A submarine would dive to escape an aircraft, run silent at depth for 30 minutes, then surface in what should have been a clear area. Moments later, the aircraft would return, attacking from the exact direction the submarine had travelled while submerged. The Germans didn't know about sonobuoys. Allied security around the devices was absolute. They were codenamed High T by the British. American forces simply called them CRT-1s, a designation that revealed nothing. When sonobuoys were captured or washed ashore, they were disguised to look like weather buoys or rescue beacons. German intelligence analysed several captured units, but failed to understand their true purpose. The Kriegsmarine assumed the Allies had developed some form of airborne magnetic anomaly detector, far more sophisticated than it actually was. They never suspected that aircraft were literally listening to them through devices floating on the surface miles away. By mid-1943, sonobuoy production had ramped up dramatically. The Navy alone ordered 150,000 units. Improved models featured better hydrophones, longer battery life up to 6 hours, and the ability to transmit on one of 6 different radio frequencies. This multi-channel capability meant aircraft could deploy multiple sonobuoy patterns and monitor them simultaneously. The tactical applications expanded rapidly. Convoy escorts began using sonobuoys proactively, dropping barriers of them ahead of convoys to detect lurking U-boats. Aircraft on anti-submarine patrol would lay sonobuoy fields across known U-boat transit routes. Hunter-killer groups centered around escort carriers used sonobuoys to track submarines across vast stretches of ocean. The most effective tactic involved deception. An aircraft would spot a U-boat on the surface and make an obvious attacking run. The U-boat would crash dive, and the aircraft would appear to lose contact, flying away as if giving up the hunt. In reality, the aircraft had dropped sonobuoys during its departure. The devices, small and difficult to see from underwater, would settle on the surface unnoticed. The U-boat captain, believing he had escaped, would eventually surface to recharge batteries. The sonobuoys would immediately detect the submarine running its diesel engines. The aircraft, loitering just beyond visual range, would receive the signal and return for a devastating surprise attack. German submariners called it the ghost aircraft phenomenon. A plane would disappear over the horizon, and the crew would breathe easier, believing they were safe. Then, 20 minutes or an hour later, the same aircraft would appear from a different direction, attacking with uncanny precision. U-boat crews began to dread surfacing. The ocean, once a sanctuary, felt like it was watching them, which, in a very real sense, it was. The psychological impact was profound. U-boat effectiveness depended on the crew's confidence in their vessel's stealth. When that confidence eroded, hesitation crept in. Captains delayed surfacing, even when batteries were critically low. They ran submerged longer than was safe, risking battery depletion and the inability to escape if attacked. The stress took a toll. By 1943, German submariners suffered casualty rates approaching 75%. Every patrol was likely to be their last. The technological cat-and-mouse game intensified throughout 1943. Germany introduced the schnorkel, a breathing tube that allowed submarines to run diesel engines while submerged at periscope depth. This should have neutralized the sonobuoy threat. Submarines could now recharge batteries without surfacing, making them invisible to visual detection and radar. But schnorkels created their own acoustic signatures. The diesel engines were loud, and the schnorkel valve opening and closing to prevent water ingestion created a distinctive rhythmic sound. Sonobuoys detected schnorkel-equipped submarines as easily as surfaced ones. The Germans developed quieter electric motors and rubber coating for propellers to reduce cavitation noise. They instituted strict silent running procedures when submerged. None of it mattered. The sonobuoys were too sensitive, the operators too well trained. By June 1943, the expendable radio sonobuoy was officially approved by the US Navy for use on all aircraft engaged in anti-submarine warfare. Every patrol bomber, every blimp, every carrier-based aircraft carried them. The Bay of Biscay, the body of water U-boat crews had to cross between their French bases and the Atlantic hunting grounds, became known as the Valley of Death. Allied aircraft saturated the area with sonobuoys. German submarines attempting the transit were detected, tracked and attacked with relentless efficiency. In July 1943 alone, 37 U-boats were sunk, many with the help of sonobuoy detections. One of the most significant operations involving sonobuoys came during the Normandy invasion in June 1944. Admiral Karl Dönitz, commanding the German U-boat force, had alerted 58 submarines to attack the invasion fleet. Allied planners knew the U-boats were coming and deployed an unprecedented anti-submarine screen. Aircraft patrolled every approach to the English Channel, each carrying full loads of sonobuoys. The statistics from Allied records are stark. Every 35 minutes, an aircraft inspected the entire defensive zone. All aircraft had microwave radar and sonobuoys. The ocean around the invasion beaches became an impenetrable acoustic barrier. Of the 58 U-boats Dönitz alerted, not one reached the invasion area. Several were detected by sonobuoys and sunk. The rest were driven off or forced to remain submerged until their batteries died and they had to surface far from the invasion fleet. The technology continued evolving. In February 1943, designers began work on a directional sonobuoy, the AN-CRT-4. This model featured a rotating hydrophone that could determine not just that a submarine was nearby but exactly where it was. The directional beam swept 360 degrees every 12 to 20 minutes, depending on sea conditions. When the rotating hydrophone picked up submarine sounds, it would be pointing at the source. This eliminated the need for multiple buoys to triangulate position. A single directional sonobuoy could locate a submarine with precision. The NCRT-4 didn't undergo full testing until early 1945, too late to significantly impact the war, but it represented the future of anti-submarine warfare. The stories of individual encounters reveal the human dimension of this technological warfare. On May 5, 1945, 3 days before Germany's surrender, U-853 torpedoed and sank the American collier Black Point off Rhode Island. It was the last American merchant ship sunk in World War II. Within hours, a hunter-killer group assembled. 4 warships converged on the area. The destroyer USS Erickson, destroyer escorts USS Amick and USS Atherton, and the patrol frigate USS Moberly formed a search pattern. The submarine had gone to ground, lying motionless on the bottom at 18 fathoms. The warships detected it with sonar and began dropping depth charges. The U-boat tried to flee, then tried hiding completely still. Neither tactic worked. The sonar held contact. On the morning of May 6th, Navy blimps K-16 and K-58 arrived from Lakehurst, New Jersey. The blimps used their magnetic anomaly detectors to locate oil slicks from damaged tanks. Then they dropped sonobuoys. The hydrophones picked up sounds of machinery, of men moving inside the pressure hull, of compressed air being released. The sonobuoys confirmed what the sonar was reporting. The submarine was still there, still alive. The warships renewed their attack with depth charges and hedgehog bombs. More debris floated to the surface: planking, life rafts, charts, clothing, an officer's cap. Finally, silence. U-853 and her entire crew of 55 men were lost. She was one of the last U-boats sunk during the war. The sonobuoy played a supporting role in that engagement, confirming sonar contacts and guiding the final attacks. But in hundreds of other encounters throughout 1943, 1944 and 1945, sonobuoys were the primary detection method. They found submarines that would otherwise have escaped. They tracked submarines through areas where surface ships couldn't operate. They turned the vastness of the ocean from an advantage for submarines into a liability. Every sonobuoy deployment created an electronic ear listening for the telltale sounds of propellers, pumps and diesel engines. German U-boat crews learned to fear the ocean's silence, because in that silence they could be heard. The statistics paint a clear picture of sonobuoy effectiveness. From October 1942 through the end of the war, the US Navy ordered 150,000 sonobuoys and 7,500 receivers. Approximately 40% of all submarines destroyed during the war were sunk by aircraft or by aircraft working with surface ships. While sonobuoys weren't the only detection method, they were present in a significant percentage of those kills. The devices proved equally effective in the Pacific theatre. American submarines were quieter and better built than their German counterparts, but Japanese submarines were not. The Imperial Japanese Navy's submarines were large, noisy, and operated with less sophisticated tactics than the Germans. Sonobuoys, deployed by aircraft operating from escort carriers and island bases, detected Japanese submarines attempting to infiltrate American-controlled waters. The most dramatic Pacific sonobuoy engagement occurred on June 23, 1944. The Japanese submarine I-52 was attempting to rendezvous with German U-boat U-530 in the mid-Atlantic to receive a radar detector and German liaison officers for transit through the Bay of Biscay to occupied France. I-52 carried a cargo of rubber, tin, opium and gold, payment for German technology. An American hunter-killer group built around escort carrier USS Bogue received intelligence about the rendezvous. Aircraft from the carrier, equipped with Sonobuoys and the new Mark 24 acoustic homing torpedo, located I-52 on the surface at night. The submarine crash-dived when radar detected the approaching aircraft. Lieutenant Commander Jesse Taylor dropped a Mark 24 torpedo and a pattern of sonobuoys. Within minutes, the sonobuoys detected sounds of an explosion and hull breaking up. But when Taylor's relief arrived, sonobuoys picked up faint propeller sounds in the area. A second Mark 24 was dropped, where the sonobuoys indicated the submarine to be. This time, the sounds of destruction were unmistakable. All 95 crew members, 14 passengers, and 3 German personnel aboard I-52 were lost. Years later, analysis of the sonobuoy recordings revealed something unexpected. The initial propeller sounds were not from I-52 but from U-30, nearly 20 miles away. The sounds had reached the sonobuoys through a surface duct, a quirk of underwater sound propagation that traps sounds in a channel near the surface and transmits them for many miles. The acoustic conditions had been perfect for detection, but imperfect for localization. It didn't matter. The submarine was still sunk, still lost with all hands. The incident highlighted both the power and the limitations of sonobuoy technology. In post-war interrogations, captured German submariners were asked about Allied anti-submarine tactics. Their responses revealed that they had never fully understood how they were being detected. Some mentioned ghost aircraft. Others spoke of impossible accuracy in Allied attacks. Many noted that diving no longer provided safety. But few connected these phenomena to Sonobuoys. The devices had been too small, too easy to miss, deployed too far from the submarine to be noticed. The Germans had been hunted by technology they didn't even know existed. Post-war analysis by Allied researchers confirmed that Sonobuoys had been one of the decisive tools in defeating the U-boat threat. They hadn't won the Battle of the Atlantic alone. Improved radar, code-breaking, long-range patrol aircraft, escort carriers, and sheer industrial production all contributed. But Sonobuoys provided the critical capability that closed the detection gap. Before Sonobuoys, aircraft could find submarines on the surface but lost them when they dived. Surface ships could detect submarines underwater, but couldn't cover enough area to protect convoys effectively. Sonobuoys allowed aircraft to maintain underwater contact, guiding surface ships to exact locations or attacking directly. The combination was lethal. By August 1943, U-boat losses exceeded their rate of replacement. By early 1944, the U-boat threat had been effectively neutralized. Germany continued building submarines and sending them to sea, but they achieved minimal results at catastrophic cost. Of approximately 1,200 U-boats commissioned during the war, 785 were lost. Of roughly 40,000 German submariners who went to sea, 28,000 never returned. It was the highest casualty rate of any branch of any military service in World War II. The sonobuoy technology developed during World War II became the foundation for modern anti-submarine warfare. Post-war development continued, driven by the Cold War and the Soviet submarine threat. Directional sonobuoys became standard. Active sonobuoys that transmitted sonar pings rather than just listening passively were developed. Miniaturization reduced size and weight while improving performance. Modern sonobuoys can operate for days rather than hours, transmit data digitally rather than through analog audio signals, and provide precise submarine locations from a single buoy. They remain one of the most effective tools for submarine detection, used by every major navy in the world. But the core concept hasn't changed since Philip Mason dropped those first prototypes from a bridge in Connecticut. A self-contained acoustic sensor, air-deployed, floating on the surface, listening underwater, transmitting data to hunters above. Simple, effective, deadly. The German submariners who ignored those first sonobuoys, who never recognized them as the threat they represented, paid the ultimate price. By the time German intelligence understood what sonobuoys were and how they worked, it was too late. The acoustic net had been cast across the Atlantic, the Mediterranean, the English Channel, and the approaches to Fortress Europe. The submarines that once prowled with near impunity, that once threatened to starve Britain into submission, that once held the balance of power in the Battle of the Atlantic, were trapped. Not by depth charges or torpedoes or superior tactics. They were trapped by sound, by their own propellers cavitating in the water, by their diesel engines growling at periscope depth, by the subtle noises of machinery that couldn't be silenced. The ocean had become transparent, and in that transparency there was nowhere left to hide. On March 7, 1942, when Navy blimp K-5 dropped that first operational sonobuoy into Long Island Sound, the men aboard probably didn't understand the significance of what they were testing. They were just trying to solve a technical problem, trying to build a tool that might help win a war. They succeeded beyond anyone's expectations. The small cylinder that splashed into the water that day was more than a piece of equipment. It was a revolution. It transformed naval warfare. It turned the invisible visible, and in doing so it helped ensure that the convoys got through, that Britain survived, that D-Day succeeded, that the war was won. 40,000 German submariners went to sea. 28,000 never came home. They were lost to many causes, to depth charges and hedgehogs and torpedoes, and accidents and disease. But thousands of them were found first by sonobuoys, by the acoustic ghosts floating on the surface, listening in the depths, reporting every sound, every movement, every desperate attempt to escape. The U-boat crews called them ghost aircraft, impossibly accurate attacks, phantom hunters that saw through water and steel. They never understood that they weren't being watched from above, they were being heard from below, and once heard, they were doomed. The sonobuoy had spoken, and the Atlantic belonged to the Allies. The transformation in Allied anti-submarine warfare accelerated through late 1943 and into 1944, driven by innovations that made sonobuoys not just effective, but overwhelming. The original AN-CRT-1 had been a crude instrument, capable only of detecting sounds and transmitting them. But by September 1943, the Radio Sonobuoy Laboratory at Columbia University had developed the AN-CRT-3, a revolutionary improvement that would fundamentally change how aircraft hunted submarines. The CRT-3 introduced calibrated frequency response, meaning operators could distinguish between different types of sounds with unprecedented precision. A surfaced U-boat running diesel engines produced a characteristic low-frequency rumble between 50 and 200 Hz. A submerged submarine running on electric motors generated higher frequency sounds from 400 to 800 Hz, along with distinctive tonal patterns from reduction gears and propeller cavitation. The schnorkel valve, opening and closing to prevent water intake, created a rhythmic pulse between 1 and 3 Hz that was unmistakable once operators learned to recognize it. Training programs established at naval air stations taught operators to identify these acoustic signatures. Men sat in darkened rooms wearing headphones, listening to recordings of actual submarine sounds mixed with ocean noise. They learned to filter out biologics, the clicks of shrimp, the songs of whales, the grunts of fish. They learned to recognize machinery sounds, propeller cavitation, hull creaking under pressure changes, the distinctive whine of electric motors under load. The education process was rigorous and continuous. As German submarines adopted quieting technologies, new acoustic signatures emerged. The latest U-boat models featured rubber-coated propellers that reduced cavitation noise. They installed sound-dampening mounts on machinery. They operated at slower speeds to minimize propeller noise. None of it provided more than temporary advantage. Allied acoustic analysts recorded every new sound, analyzed its characteristics, and distributed training materials to operational squadrons within weeks. By early 1944, experienced sonobuoy operators could identify not just that a submarine was present, but what type it was, whether it was running on diesels or electric motors, approximately how deep it was running, and which direction it was heading. The ocean was becoming not just transparent but legible. The tactical employment of sonobuoys evolved into sophisticated operational art. Early deployment patterns had been simple: drop several buoys in a circle around the submarine's last known position and wait. By mid-1943, patrol squadrons were using barrier patrols, lines of sonobuoys deployed across suspected U-boat transit routes. A typical barrier consisted of 12 to 16 buoys spaced at 2-mile intervals, creating an acoustic fence 24 to 32 miles long. German submarines attempting to cross these barriers on the surface or at schnorkel depth would be detected by at least one buoy. The aircraft monitoring the barrier would receive the signal, calculate an intercept course, and arrive at attack position within minutes. The Germans tried everything to defeat these acoustic barriers. They attempted to slip through submerged at slow speed on electric motors, hoping to minimize acoustic signature. This sometimes worked but required extraordinary discipline. A submarine moving at 2 knots underwater could take 12 hours to transit a 24-mile barrier. Any sound louder than a whisper inside the pressure hull could be detected. Any machinery malfunction that created unusual noise meant certain detection. The psychological strain on crews attempting silent transits was immense. Men moved in slow motion, communicating only through hand signals. Equipment was secured to prevent rattling. Even cooking was suspended because the sounds of pots and utensils could betray their position. For 12 or 15 hours the crew would barely breathe, listening to the sonar pings from hunting ships above, wondering if the next depth charge pattern would find them. Some U-boat captains attempted high-speed surface runs through the barriers at night, gambling that they could cross before aircraft could respond to sonobuoy detections. This was suicidal. Aircraft equipped with radar and searchlights would detect the surface submarine within minutes of the sonobuoy alert. The submarine would crash dive, but by then the aircraft had its position. Depth charges or acoustic homing torpedoes would follow. Very few submarines survived high-speed barrier transits. By December 1943, U-Boat Command had issued explicit orders: do not attempt to force the Bay of Biscay barriers. Take the long route around Spain and Portugal. Stay deep during the day, surface only at night in heavy weather when aircraft cannot operate effectively. These orders reflected complete defeat of Germany's submarine strategy. The direct route across the Bay of Biscay took 3 days. The circuitous southern route took 2 weeks, consuming fuel that should have been used on patrol, exposing the submarine to additional hazards and dramatically reducing time on station in the Atlantic hunting grounds. The Allied anti-submarine campaign achieved such dominance that by early 1944, German U-boats were no longer even attempting to attack convoys in most areas. Instead, they were focused purely on survival, trying to reach patrol areas and return to base without being destroyed. The hunter had become the hunted. The statistics from German naval records captured after the war reveal the catastrophic decline in U-boat effectiveness. In 1942, German submarines sank an average of 96 Allied ships per month. In 1943, that number dropped to 50 ships per month. By 1944, it was 25 ships per month. In the first 4 months of 1945, U-boats sank a total of 31 ships, fewer than they had sunk in any single month during 1941. Meanwhile, U-boat losses continued to climb. In 1943, Germany lost 244 submarines. In 1944, they lost 249. By any measure, the U-boat force had been defeated. Sonobuoys played a direct role in numerous confirmed submarine kills. While exact attribution is difficult because most sinkings involved multiple detection methods and weapons, Allied records document hundreds of engagements where sonobuoys provided initial detection or maintained contact during attack runs. One particularly notable engagement occurred on August 12, 1944, when aircraft from USS Bogue sank U-29 in the North Atlantic. The submarine had been proceeding submerged at schnorkel depth when a patrolling TBM Avenger detected it visually, spotting the schnorkel wake. The U-boat immediately dove to 400 feet and attempted to evade. The Avenger pilot, Lieutenant Richard Cormier, dropped a pattern of 6 sonobuoys in a hexagon around the submarine's last position. Within 3 minutes, 2 of the buoys detected propeller sounds indicating the submarine was moving northeast at approximately 4 knots. Cormier vectored in 2 additional Avengers carrying acoustic homing torpedoes. The submarine, detecting the torpedo's approach, went to emergency deep, exceeding 600 feet. The acoustic homing torpedoes, equipped with depth-keeping mechanisms, followed. The sonobuoys recorded the sounds of explosions, then the unmistakable noise of hull collapse under extreme pressure. Debris surfaced hours later, confirming the kill. All 56 crew members were lost. This engagement demonstrated the evolved lethality of Allied anti-submarine tactics. Visual detection, sonobuoy tracking, acoustic torpedoes, and coordinated multi-aircraft attacks created a kill chain that submarines could not escape. The ocean's depth, once a refuge, had become a trap. Going deep meant slow movement, which meant sonobuoys had more time to detect and track. Staying shallow meant vulnerability to visual detection and radar. There was no winning move. Perhaps the most psychologically devastating aspect of sonobuoy warfare was the uncertainty it created for German crews. A submarine could be running submerged, all systems operating normally, no indication of pursuit. Unknown to the crew, an aircraft 5 miles away had dropped sonobuoys 20 minutes earlier. The hydrophones were listening. The submarine's propeller noise was being transmitted to the aircraft. The pilot was calculating attack parameters. The first indication the submarine crew would have of danger was when depth charges or acoustic torpedoes began exploding around them. There was no warning, no chance to evade, no opportunity to fight back. Just sudden, catastrophic violence from above. German submariners developed superstitions around this phenomenon. Some crews believed certain areas of the ocean were cursed, that submarines disappeared there without explanation. Others attributed the attacks to spies within the U-boat service, claiming that Allied intelligence knew their exact routes and schedules. A few suspected the truth, that the Allies had developed some form of listening device, but without understanding the mechanism, they couldn't develop effective countermeasures. The Kriegsmarine scientific establishment conducted extensive research into Allied detection capabilities. They knew about radar and understood how it worked. They developed radar detectors that could warn of approaching aircraft. They created radar-absorbing coatings for submarines. They designed schnorkels with minimal radar cross-sections. All of these measures focused on defeating radar because that was the threat they understood. They never solved the sonobuoy problem because they never fully comprehended what sonobuoys were or how extensively they were being deployed. A captured German technical intelligence report from January 1945, found in Kriegsmarine archives after the war, includes a section on Allied anti-submarine capabilities. The report mentions small floating devices occasionally observed in areas of submarine activity. The analysis concludes these are probably weather monitoring buoys or rescue beacons. The report notes that Allied aircraft seem to possess detection capabilities that exceed known radar performance, but attributes this to superior radar technology, rather than acoustic methods. Even 9 months before the war ended, German intelligence fundamentally misunderstood the primary tool being used to destroy their submarines. This intelligence failure had catastrophic consequences. Because the Germans didn't understand sonobuoys, they couldn't train crews to recognize or avoid them. They couldn't develop tactics to defeat them. They couldn't create technical countermeasures. They were fighting an enemy they couldn't see and didn't understand. The introduction of the Mark 24 acoustic homing torpedo in March 1943 created a synergistic relationship with sonobuoys that was absolutely lethal. The Mark 24, codenamed Fido, was essentially an acoustic-seeking torpedo that would home on submarine propeller noise. It could be dropped from aircraft and would circle while descending, listening for submarine sounds. When it detected a target, it would chase until impact or fuel exhaustion. Combined with sonobuoy detection, the Mark 24 was devastating. An aircraft would use sonobuoys to locate a submarine, then drop the Mark 24 in the vicinity. The sonobuoys would continue tracking the submarine while the torpedo hunted. The aircraft could hear through the sonobuoys when the torpedo acquired the target and when it struck. This combination accounted for 37 confirmed submarine kills during the war, an extraordinary success rate for a weapon system that was used operationally for only 2 years. Lieutenant Commander George Ingram, flying a TBF Avenger from USS Card, achieved one of the most dramatic Mark 24 kills on August 2, 1943. His aircraft detected U-664 on the surface southeast of the Azores. The submarine crash-dived immediately. Ingram dropped 4 sonobuoys around the crash-dive position, then orbited while monitoring. Within 6 minutes, 2 sonobuoys detected propeller noise, indicating the submarine was moving south-southeast at approximately 3 knots at a depth of about 250 feet. Ingram calculated a lead angle and dropped a Mark 24 torpedo 800 yards ahead of the submarine's projected path. The sonobuoys recorded the torpedo's high-pitched propeller sound as it circled and descended. Then the tone changed. The torpedo had acquired the target and was accelerating. 23 seconds later, the sonobuoys recorded a massive explosion. The submarine's propeller sounds ceased abruptly. Subsequent sounds of air escaping and metal creaking under pressure confirmed the kill. U-664 and all 52 crew members were lost. The efficiency of this kill was terrifying from the German perspective. From crash dive to destruction, only 11 minutes had elapsed. The submarine had no warning, no opportunity to evade, no chance to deploy countermeasures. The crew's last moments would have been spent in darkness at depth, hearing the approaching torpedo, knowing they were about to die, unable to do anything to prevent it. This scenario repeated dozens of times throughout 1943 and 1944. Submarines would be detected by sonobuoys, tracked as they attempted to evade, then killed by acoustic torpedoes guided to their positions by the same sonobuoys that had found them. The combination was so effective that by late 1944, U-boat crews called the Mark 24 the Zaunkönig Hunter, their own name for their acoustic torpedoes turned back on them with bitter irony. The scale of sonobuoy deployment by 1944 was staggering. A single patrol bomber might carry 18 to 24 sonobuoys on a mission. With multiple aircraft operating from each base, and dozens of bases around the Atlantic and Mediterranean, thousands of sonobuoys were being deployed daily. Production records show that by June 1944, over 100,000 sonobuoys had been manufactured. By war's end, the total exceeded 150,000 units. Each sonobuoy represented a small but significant investment in materials and labour. The radio transmitters required vacuum tubes, precision components that were in high demand for other military applications. The batteries used scarce materials, including zinc and mercury. The hydrophones required precision machining and careful calibration. Yet the devices were completely expendable. Once deployed, they operated until their batteries died, then sank and were never recovered. This expendability was itself a demonstration of American industrial capacity. Germany could never have afforded such waste. Every piece of equipment had to be recovered, repaired, reused. The idea of dropping thousands of Sophisticated electronic devices into the ocean to be used once and discarded would have been incomprehensible to German logistics officers. But America's industrial base could absorb this cost easily. The Sonobuoys were mass-produced on assembly lines by workers who had been making radios or electronics components before the war. The manufacturing process was so refined that by 1944, the per-unit cost had dropped to approximately $180, equivalent to about $3,000 today. For that price, the Allies bought the ability to detect submarines that might otherwise sink multiple cargo ships, carrying war materials worth millions. The return on investment was extraordinary. The psychological impact on Allied pilots and aircrews was equally significant. Before Sonobuoys, anti-submarine warfare had been frustrating and largely ineffective. Pilots would spend hours over empty ocean, occasionally spotting a submarine, watching it dive, then being forced to guess where it might surface. Most patrols ended with no contact and no results. The introduction of Sonobuoys changed everything. Now pilots had a tool that let them maintain contact with submerged submarines. They could track their movements, predict their positions, and execute precise attacks. Success rates climbed dramatically. Pilot morale improved correspondingly. Anti-submarine squadrons developed fierce competition over kill scores. Successful pilots were celebrated as heroes. Tactics and techniques were refined and shared across units. An entire culture of submarine hunting emerged, supported by the technology that made hunting effective. Training programs evolved to maximize sonobuoy effectiveness. New pilots and radio operators attended schools where they learned acoustic theory, submarine behavior, oceanography, and tactical employment. They practiced in exercises where friendly submarines played the role of enemy U-boats, attempting to evade detection while aircraft hunted them with sonobuoys. These exercises revealed weaknesses in tactics and equipment, driving continuous improvement. By 1944, the average sonobuoy operator could identify submarine types by sound alone, estimate depth and speed from acoustic signatures, and predict evasion maneuvers based on years of combat experience compressed into intensive training. The human element was as important as the technology. Sonobuoys provided the data, but skilled operators interpreted that data and turned it into actionable intelligence. The impact extended beyond direct submarine kills. The mere presence of sonobuoys forced German submarines to operate under constant stress and restriction. U-boat captains knew that surfacing or running at schnorkel depth anywhere near Allied convoy routes or patrol areas risked detection. This forced them to operate submerged on battery power for extended periods, drastically reducing their operational range and effectiveness. A submarine that might have been able to patrol for 8 weeks was forced to return to base after 4 weeks because battery limitations prevented aggressive operations. The reduction in patrol time translated directly to reduced Allied shipping losses. Fewer submarines on patrol meant fewer opportunities to attack convoys, even if those submarines survived their patrols. German U-boat production continued at high levels through 1944 and into early 1945, but the submarines being produced couldn't be effectively employed. They were sunk during training exercises in the Baltic. They were destroyed in transit to operational areas. They were caught at schnorkel depth in supposedly safe zones. The Kriegsmarine built 155 U-boats during the war. At the time of German surrender in May 1945, 375 submarines were still operational. But operational didn't mean effective. Most of those submarines were trapped in port, unable to put to sea because the acoustic barriers and patrol zones made any transit suicidal. The boats sat idle, their crews waiting for orders that would never come, while Allied ships crossed the Atlantic unmolested. One of the final sonobuoy-related engagements of the European War occurred on April 29, 1945, 8 days before Germany's surrender. U-1017, a Type 7 D&C submarine, was detected by sonobuoys while attempting to transit the English Channel. The submarine was en route to Norway, fleeing the Allied advance into Germany. A RAF Liberator bomber detected the submarine with radar, then dropped sonobuoys when it crash-dived. The sonobuoys tracked the submarine for over 3 hours as it attempted to reach deeper water. Eventually, running low on battery power, U-1017 was forced to surface. The Liberator attacked immediately with depth charges, forcing the submarine to dive again. More sonobuoys were deployed. The acoustic tracking continued. Finally, with batteries completely exhausted, the submarine surfaced and the crew abandoned ship. Demolition charges were set, and U-1017s sank in shallow water. The crew was rescued and became prisoners of war. They were among the lucky ones. In the Pacific theatre, sonobuoys played a different but equally important role. Japanese submarines were generally larger and noisier than German U-boats, making them easier to detect acoustically. But the vast distances of the Pacific meant that patrol aircraft coverage was less dense than in the Atlantic. Sonobuoys extended the effective search area of each aircraft dramatically. A patrol bomber could deploy a barrier of sonobuoys across 30 miles of ocean, then patrol other areas while the buoys listened. If any sonobuoy detected a submarine, the aircraft would return immediately to prosecute the contact. This force multiplication was critical in an area where aircraft were scarce and patrol areas were enormous. The Imperial Japanese Navy lost 128 submarines during the war, approximately 75% of their total submarine force. American aircraft, often employing sonobuoys, accounted for a significant percentage of these losses. Japanese submarine tactics were less sophisticated than German tactics, and Japanese submarines operated with less stealth, making them relatively easy targets once detected. American submarines were the primary threat to Japanese shipping, but American anti-submarine forces ensured that Japanese submarines posed minimal threat to American naval operations. The asymmetry was dramatic. American submarines ravaged Japanese commerce, while Japanese submarines achieved little. Sonobuoys, while not the only factor, contributed significantly to this imbalance. Post-war assessment of sonobuoy effectiveness concluded that the devices had been one of the most significant technological developments in anti-submarine warfare. For relatively modest investment in research, development and production, the Allies had gained a capability that fundamentally altered the submarine warfare equation. The United States Navy's Official History of Anti-Submarine Warfare, published in 1951, stated that expendable sonobuoys, in combination with improved radar, acoustic torpedoes, and increased air patrol coverage, reduced U-boat effectiveness by an estimated 60 to 70% compared to what it would have been without these technologies. British naval historians reached similar conclusions. The Battle of the Atlantic had been won through multiple factors, but sonobuoys represented a technological leap that submarines simply couldn't counter. The lessons learned from World War II sonobuoy operations shaped Cold War anti-submarine warfare doctrine. The Soviet Union possessed the world's largest submarine fleet, and those submarines represented a primary threat to NATO naval operations. American and British naval forces developed increasingly sophisticated sonobuoy systems explicitly designed to detect and track Soviet submarines. Directional sonobuoys became standard. Active sonobuoys that emitted sonar pings and listened for echoes were developed. Sonobuoys that could remain operational for days rather than hours were fielded. Digital data transmission replaced analog audio signals. Processing algorithms automatically filtered background noise and identified submarine acoustic signatures. Modern sonobuoys are technological marvels compared to the crude devices Philip Mason tested in 1942, but they serve exactly the same purpose. Today's anti-submarine aircraft carry dozens of sonobuoys and can deploy complex patterns optimized for specific ocean conditions and submarine types. Helicopters operating from ships deploy sonobuoys to extend their search radius. Underwater autonomous vehicles can deploy sonobuoys in areas too dangerous for aircraft. The technology has proliferated globally. Every major navy operates some version of sonobuoy systems. The fundamental concept has proven so effective that it remains relevant 80 years after its invention. The German submariners who faced the first sonobuoys in 1942 and 1943 couldn't have imagined how completely this technology would dominate their world. They went to war expecting to fight surface ships and aircraft in a contest of stealth versus vigilance. Instead, they found themselves in a battle against the ocean itself, against devices that turned water into a conductor of sound and made depth irrelevant as a defense. They adapted as best they could, developing quieter submarines and better tactics. But adaptation has limits when facing overwhelming technological and industrial superiority. By the time German intelligence finally understood what sonobuoys were and how they worked, the war was effectively over. Even if they had understood earlier, there were no effective countermeasures. You cannot hide from sound in water. You cannot silence machinery that must operate for the submarine to function. You cannot escape detection when hundreds of listening devices blanket the ocean. The Germans had been trapped not by superior strategy or braver sailors, but by physics and engineering and industrial capacity. The sonobuoy was a perfect expression of Allied material superiority. Take a simple concept, listening for submarines underwater, apply engineering to miniaturize and automate it, manufacture it by the thousands, deploy it everywhere, accept losses as the cost of doing business, iterate and improve relentlessly. This approach won the Battle of the Atlantic. It won the air war over Europe. It won the war in the Pacific. It won World War II. 40,000 German submariners went to war. 28,000 died. They were brave men fighting for a cause that history would judge harshly, but their bravery was real. They faced dangers that few people can imagine, descending into darkness under hundreds of feet of water, knowing that detection meant death, that every dive might be their last. They fought with courage and determination until the ocean became so hostile that courage wasn't enough. The sonobuoy made the ocean hostile. It turned sanctuary into death trap. It gave Allied forces eyes that could see through water and darkness, and in the end it helped ensure that the submarines which once terrorized the Atlantic were hunted to near extinction. The technology developed in desperate response to crisis became one of the decisive weapons of the war, small, expendable, floating on the surface, listening in the depths, transmitting death. The German submarine crews ignored them, dismissed them, never understood them until it was too late. By then, they were trapped in an acoustic net that covered the ocean, and there was no escape.